Hello everyone. In this tutorial, we'll see about coding the concept of logistic regression. Okay, so the programming language will be following the Python. Okay, so let's start with that and start with importing a very important file which will have all the mathematical operations. So it's input numpy as np, and sometimes we would be required to plot the values, so we can import matplotlib dot pyplot as plt. Okay, we are done with that. And now, so the basic of logistic regression is based on the idea of sigmoidal function. So somewhere we need to have a sigmoidal function. So let's create a sigmoidal function and see. So let's create a function and then sgmf, and that sigmoidal function should take the input value x, and if output is y, then the formula says that sigmoidal of any value is 1 upon 1 plus exponential, so np.exp exponential of minus x, and that's it, return O. Okay, so let's call it from somewhere, and for that we need to have some input samples. Okay, so let's create input sample. X is equal to np.arrange from minus 10 to plus 10 with the interval of 0.2. We'll have total 100 points here. And output, maybe its output is so that is going to be observed output. So observed output is list, for example. Okay, so this is a x. Let's execute and see. Save it first. Okay, 5. Yeah, so you can see that x is 100 values, y not is a blank list. Let's iterate through all the samples of x for I in range 0 comma length of x, and we'll have some observed value of this function that will append in the list, and inside that we'll call the function sigmoidal function SCMF, and we'll transfer the each of the samples here. So here are the list of x and y not. The both are here. Let's execute. So y underscore it's a O and I put it 0. Save it and execute. Yeah. So y not is a 100 value, x is 100 values. Let's check it out. How is it looking? So plt dot plot x comma y, execute x comma y underscore. Oh, that is observed. It's not correct. Because I think this has made it wrong. Yeah, after putting this and so here is the sigmoidal function. You can see that I have very well shaped, and the value of sigmoidal function varies from 0 to 1. That's fine so far. That means our sigmoidal functions formula is fine and it is working. Okay, now let's delete it. Okay, in logistic regression, it will, like any other machine learning algorithm, it will require two things, that is weight and the input samples. Along with that, it requires the true labels also, as it's a part of a supervised learning technique. So based on the true label, it will try to adjust the weight. So let's create the dataset. So dataset here is, suppose we are having a 2-dimensional input. So x is going to have 2-dimensional value, np.random.rand and let's say it's having 10 samples. Each sample is of 2 dimensions. Okay, so this is going to be our weight, our input sample. For each input sample, we need the y value, that is a true label. Let's say we have the y value randomly one. It could be either 0 or 1. 1 1 1, maybe 0, maybe 1, maybe 0 0 1, maybe 0. It should have 10 values: 1 2 3 4 5 6 7 8 9 10. So one additional L. Okay, perfect. So we are having x, we are having y. Now we need to consider weight, and that weight needs to be adjusted according to this true label. Okay, so because we are having two-dimensional input, so weight value will have the two values only, and it will be can be randomly created at np.random dot rand with two values and one biases. Biases are quite important. Rand, that is of 1. Bias need to be of value 1. So this is how weights and biases all are created. Let us say we can check it out. We can execute it and see what is the weight. So weight is of 2 values. Bias is 1 value. Looks okay. We move forward. So first of all, what we have to do is we need to calculate the observed value. Now let's say y observed value is represented at y underscore o. Let's say it's an list. So we need to get the observed value for each input sample. So let's iterate through each input sample. Range 0 comma length of x, and we'll iterate through each sample here. We need to call the function sigmoidal function gmf for each input sample x of I. Okay. Along with that input values, what other we can have? We need to have the weight and the biases also, because here we are not just calculating the value of the function, we are thinking to give the weight to each dimension, so that the proposed function, that this is a sigmoidal function, should be very well fitted to the given data. So this is a given data, this is a sigmoidal function. We need to decide the weight, how much weight to be given to each of the input dimension. Okay, that means we need to have two more input to the sigmoidal function along with input x. Okay, so this is going to be observed value, observed dot append, and like this. Here also similarly we can make the changes, w comma b. Okay, that means this x here is not actually the x, it should be the weighted x, and that could be a different value. Okay, we'll calculate that. Maybe we say it's a value minus val, and that value will be wtx, wtx plus b. I think so. That's the equation. That's a equation of sigmoidal function is 1 upon 1 plus e raised to the power minus wtx plus b. Okay, so let's create that wtx. Wtx means the multiplication of the weight vector and the x values input vector. So x comma, so x and w both are x is what? X is a first sample. So first sample will be of dimension 2. So x is a vector, and w is a vector again. So both are the row vector. So one need to be column vector, then only we can make the multiplication. Np dot transpose. So let's take the transpose of w, right? Yeah. So this is how wtx have been created plus b, right? So that way we have got the y observed. Let's execute and see what are the values of y observed. You can see it's a numpy array. Return O. Okay. Y underscore O. If we'll see, this is the observed value. Okay, and this is a true label. So we need to find the difference, and that difference will be the loss. Okay, so in the next step we need to calculate the loss, and in this particular example we are going to consider the cross entropy as our loss function. So that cross entropy function will take the true label as input, observed value as input. Okay, and the formula says it's a y times log of y observed here comes the minus n also plus 1 minus y times log of 1 minus y observed. Okay, so this is the loss value we have calculated, and that loss value should be returned back. Correct? Yeah. Okay, so observed value we have already got. That's a loss is again a list. So we can have loss dot append. For loss, we need to give what is the first argument. First argument to the loss is y. Okay, first sample and the true label of the first sample. Next predicted label of the first sample. That's it. Yeah. So that it will keep accumulating in this loss list. Okay, when all the losses will be calculated. Okay, let's execute and see what is the loss value. Only two arguments. It says it's a loss dot append. Okay, so loss dot append and function needs to be called. We didn't call the function. That function name is cross underscore en. Yeah. So loss. Let's see here. What is that? Oh, cross underscore en underscore f. I think we didn't make any more. Log is not defined. That should be np.log. Okay. Any more log? No. Yeah, then it's fine now. So loss is having this value. Okay. In next step, we need to create the function that should calculate the gradient values, and that gradient will be actually helping us to adjust the weight. Okay, so let's have one more function, gradient here, gradient of this loss function with respect to weight. So let's say it's a grade function, and that grade takes into consideration actual value, observed value, and input x, and this formula says that it's going to be y minus y observed multiplied by x, and that return g. This is our gradient values. So how did we come up with this formula? So this formula can be checked on the tutorials where this loss function is differentiated with respect to weight, and after doing that we get to see that this the function, the expression which comes is actual value minus observed value multiplied by x. So that x will vary when we will talk about the bias. For the biases, this x needs to be 1. Okay, so let's make the difference. Let's update the weight. So this weight, new weight value will be equal to the previous weight value plus learning rate. There should be learn learn rate multiplied by this grade. value, and this weight value needs the actual y or the true label as input, the proposed, the observed value as input, and sample. For each sample we have got this update on the weight. This learning rate is to be defined, and let's say for our case learn rate is equal to 0.1, right? So that for this weight, this way we can update the weight value. Similarly for biases we can write it like b, and this x instead of x we can have 1, because for biases there's no x. Biases are actually the intercept, it doesn't have the input values, right? So that is going to be that is would be updation on weight and the w. Okay, cool. Let's see, is there any error or it's working perfectly? It is, I think it is updating well. X is of 2 in dimension, fine. Y w is fine. B looks okay. Okay. Let's create the what to say, let's check out what is the average loss through across all these samples. So loss is equal to np dot mean loss. Okay, and we need to put this under epochs. So this is what happened through all the samples of the given data set in one epoch. So I may need multiple epoch in order to get the better values of the weight and the biases. Okay, so for epoch 0, 10, and that's, I think that should suffice the requirement. For the epoch we can have the losses. So for each epoch this loss value should keep reducing. Okay, let's see what happens. Here you can see it has got some random input values x and randomly assigned y value, and here it is started from 0.67, 0.66, 6529. So you can see that it is reducing. So maybe like we can have some one other execution. It started from 0.70 and ended with 0.62. So here like we can see that the weights are actually updated, and the observed value is getting changed, and so the observed value of a y is going closer to the actual label, hence the losses are decreasing with epochs. So when we can have the exhaustive epoch in the sense like good enough number of the epochs so that we can guarantee that we have actually reached up to the global minima. From there we will pick this w and the b values, and this w and b we are having, we will supply this SDMF function. X could be our testing data, w and b are given, then whatever the output will be having, that will be our test performance. So that's it about the basic code of logistic regression.